Welcome. This video is going to talk about examples of collisions between objects in linear motion and objects that are purely rotational. So in this example, I want to talk about what happens if a child runs up to a merry-go-round, grabs onto a handle right at the end of the merry-go-round. Well, we know from hopefully doing this as a child, if you had a fun childhood like me, that once you grab onto that merry-go-round, you start spinning in a circle. Now, you weren't initially traveling in a circle, you were running in a straight line. But when you grab on, you have an angular momentum because you had a linear momentum with a moment arm. Your momentum was some distance away from the center of rotation of that merry-go-round. So for any object that has linear momentum, the amount of angular momentum is just equal to the radius from the center of rotation to where our object is, crossed with the momentum of our object. So our object is a 35 kilogram child that happens to be running at 4.5 meters per second. And the child happens to connect with the merry-go-round at an angle of 120 degrees from the radius. So, that's a little nebulous if you think about it. Is it 120 degrees this way, sort of looking at the radius and heading outward? Is it 120 degrees in this way? Good news with cross products. Cross products are based off the sine. And the sine of 120 degrees is the same as the sine of 60 degrees. We get the same answer however we think about the problem. So for our merry-go-round, it has a built-in rotational inertia based on its mass, its shape, its size of 27 kilogram meters squared. And the outer radius of that merry-go-round is 1.2 meters. So if the child grabs onto the merry-go-round, we have a completely inelastic collision. Things have collided and stuck together. And those are the easy collision, because if we have multiple objects before the collision, after the collision, we only have one object. So whatever angular momentum the child has, plus whatever angular momentum the merry-go-round has, gets added together. That's going to give us our final angular momentum. And our final angular momentum is going to be based off the total inertia that we have. So for this merry-go-round, with a mass stuck to the edge, it would be the inertia of the merry-go-round plus the inertia that the child brings to the problem. Now with linear momentum, it's just mass. But here, mass and shape both matter. Now, children aren't particles. They aren't little tiny points that have no size and shape. But what we're going to assume is, compared to a piece of a playground equipment, a child's pretty small. So we're going to start by just treating this child like a particle. And for a particle, the moment of inertia is equal to the mass of the particle times the radius of the circle that particle is rotating in. So for the merry-go-round, the mass of the child we have is 35 kilograms. The radius is going to be the radius of the merry-go-round, 1.2 meters. So our total inertia then is going to be 27 kilogram meters squared plus 35 kilograms times 1.2 meters squared. That gives us the total amount of inertia we have, multiplying our final angular velocity. Now for our initial angular momentum, if the merry-go-round's stationary, we just have to worry about the angular momentum of the child. So since the child we're treating like a particle, initially traveling in a straight line, so we'd have the radius of the merry-go-round, which is the radius of the circle when this becomes a rotational problem, times the momentum of the child, the mass of the child, times the velocity of the child, times the sine of the angle between the two, which we said 120 degrees, 60 degrees, both give us the same result. So to solve for our final angular velocity, we would have the radius times the mass times the initial speed of the child times the sine of the angle between the radius and the momentum is going to equal my total angular inertia times my final angular velocity. So my final angular velocity is going to be 1.2 meters times 35 kilograms times 4.5 meters per second times the sine of 60 degrees divided by the inertia. As I said, the merry-go-round, 27 kilogram meters squared, 35 kilograms times 1.44 meters squared gets added to that, which is going to give us more than double the inertia that we started with. So our final angular velocity is going to be 2.1 radians per second. Thanks for watching.